All right, let's see if we've got two screens showing slides. That's great. So great lunch. It's always great to follow a lunch. I hope everybody filled themselves up with coffee. You only have to stay awake for another 30 minutes. After that, it's... Yeah. All right, Tino says for the rest of the day. So before I get going, I just want to thank all the folks at OpenNebula for inviting me to come here and speak, and for providing OpenNebula to the community and all the help they've given my team to help us succeed with our project. So I'll jump right in and go through some details of system testing challenges at Akamai and how we're using OpenNebula to really revolutionize how we're doing development and testing at Akamai. Some background on Akamai. Akamai is a CDN, which stands for Content Delivery Network. So we make the internet fast, reliable, and secure. We're delivering static content, streaming content, various other services to end users that are looking at websites and content online. So our customers are the websites and content providers, and our end users are all the folks out there who are staring at Facebook. So we do this with a globally distributed network of servers, either caching content close to end users or doing live streaming, as I said, and kind of at the core of that is a DNS-based load balancing system that dynamically directs end users to a server of our choosing. We operate at massive scale. So we're serving 15 to 30% of what you see on the internet is coming from an Akamai server. So that equates to over 3 trillion hits per day, 30 plus terabits of traffic, massive, massive scale. Again, over 200,000 servers in over 100 countries, thousands of software components, and hundreds of server roles. So it's a very heterogeneous environment. We don't have just one thing that we want to test. We have a range of end-user facing services running on 60 to 70% of those servers, and then a range of infrastructure services that are underpinning all of those end-user facing products that we're serving. So very heterogeneous environment. Maybe the Borg was a bad choice of an image for that reason. So this brings me to system testing at Akamai. When you have such a big, complex, heterogeneous, distributed system, system testing becomes very important. It's great to find bugs in unit test or in subsystem testing, but frequently the most important issues we have don't come out until we really put the system together and run all the pieces together. So system testing becomes really important for us. But there's some challenges there. With such a big, complicated, distributed system, we have a very complicated system test environment. And so, this is a fun cartoon showing some of the internal components that are critical to any kind of basic system testing that we might want to do at Akamai. And, putting together a system like this and operating it for testing takes a lot of effort. And we have about 3 of these in our lab that we use for testing. And it's great that we have 3 instances of Akamai that we've set up and configured, but we need more. They're a scarce resource. There's only these 3 environments, and different groups are sharing those environments to test their particular system. So I might be testing system X while someone else is testing system Y, and those systems are really dependent on each other, and so our testing can impact one another. So just to run quickly through some of the challenges we face in this system testing space, these test nets, these collections of nodes with all these different server roles installed on them, they're expensive to build, and they require a huge team to maintain. And each individual Akamai instance that we'll create is sort of an incremental cost. All of the maintenance and administration work we might do on all those different systems, we're going to have to repeat that separately for each instance of Akamai that we're running in our lab. And no one person knows how to do all that work because, literally hundreds of different server roles, thousands of different components running in this distributed system. The fact that we share these test nets means that sometimes we step on each other's toes, right? If I roll out a bug in System X and you're depending on System X for your testing, you're going to have a bad day. Sometimes the fit is poor. I may want to customize my test environment or change the configuration or behavior of my test environment, but I can't do that because I'm going to impact your testing, right? And so conflicting uses need to be coordinated. And that results in inevitable delays when we're trying to figure out where can I test, whose system can I use. There's only 3 test nets out there. How can I get access to the resources that I need, a system that's configured and functioning well enough for me to do my testing. And so that's what kind of brought out the Vtastic concept. You know, we want to provide access to more isolated testing environments, more instances of Akamai, dedicated instances of Akamai to test. And we also want to hit some of these other concepts, right? Making it easier for people to get involved with their testing, being able to maybe save the state of a system for later debugging, or save the state of a system as a consistent start point for a given system test, right? Destructive testing. On our bare metal test nets that we're managing by hand today, if we make a mess on those test nets, we have to clean that up, right? And I'm sure everybody in this room understands the possibilities for using virtualization for destructive testing. And then another one I'll hit briefly is this automation bullet. If you only have 3 test environments and people are sharing them and testing on them constantly, how do you perform continuous integration testing at the system level, right? We need the ability to spin up an instance of Akamai when somebody makes a commit or when a release is being put together and run test automation against that environment. That means it needs to be a dedicated, on-demand environment. So the Vtastic vision is to offer, you know, continuous, automated, end-to-end testing for every engineers across all those components at Akamai. And so how can we do that? You know, we started by setting up a new instance of Akamai, new instance of our distributed system. Big surprise, we set that up on VMs that are being hosted. We use KVM and QEMU, orchestrated, of course, by OpenNebula. And we've built a web application on top of OpenNebula called VRT that understands a collection of VMs as one instance of Akamai's distributed system. It has some of the Akamai-specific details baked into it, and it understands how to manage collections of VMs in this way. And so the Vtastic system works with OpenNebula to be able to shut down our testnet, save copies of all those disks onto persistent storage, and then we can boot clones of that testnet. And so we can run, you know, as many clones concurrently as our infrastructure can support. And so the idea is sort of, and I'll jump ahead briefly, you know, the idea is that we have this master testnet that we've created, and we'll go into that special set of running VMs and do our installs, make our changes, add systems, improve the testnet, and then we'll save a snapshot, shut the entire thing down, save off copies of the disk images, and expose that snapshot as the latest revision, you know, of our master testnet. And so that running clone that we're changing, we call that our master candidate. And once we're happy with it, we'll save that. That becomes the new master that we'll expose to our end users, and we can move on and sort of start our next master candidate. And while these snapshots are available in our system, you know, engineers can come and create their own clones for doing testing. They can customize those clones and save them as their own snapshots, and then, you know, maybe share them with other groups who want the latest version of software that System X is developing. So that's a bit about sort of our process for how we manage this master testnet. And frankly, you know, there's a lot of challenges on the virtualization side and on our web application side, but the biggest challenge we've faced in getting Vtastic off the ground is in building out that master testnet and getting that realism to a point where our engineers can, you know, see that as a viable option as opposed to the systems that they've been testing on. So most of the work and sort of long process and getting to where we are has actually been in managing this master testnet and setting up all those systems. Now for some of you, you know, when you were seeing my pretty picture of all these clones running on top of OpenNebula, you may have been thinking, you're going to set up this instance of all these different systems talking to each other, DNS records, all that stuff. how can you just take that whole thing and create copies of it, right? Do you re-IP all the machines and contextualize the entire thing? How is that realistic? And the answer is no, we don't. In fact, at Akamai today, each of these machines, its identity within the kind of Akamai ecosystem is the IPv4 address that we manage the machine on. And so if the machine's main IP is its identity, that means that all of these various systems that we have know each other by the machine IP. It's not even possible for us to assign unique IPs to all of these machines when we create a clone of our master testnet. And so instead we clone the entire IP space. What we do is we have this VM router that's acting as a NAT gateway, and that's really the only VM in our testnet that's customized or contextualized when we create a clone. We give that router its own unique lab reachable IP address on the outside. Every single Akamai system that's running on the inside boots from clones of these saved disk images, and it's in the exact same state that it was in when we shut it down and saved the snapshot. All the machines have the same IPs. They're talking to each other on this internal /15 and a range of massive block of IPv6 space that we have inside this VLAN. And that's how we're able to clone our entire distributed system. To be able to interact with those systems, we've developed some tools that are deployed automatically in developer environments for shell access or browser access to these testnets. You might think you could use a VPN or something like that to connect yourself to a specific instance of our private IP space. But that was a little bit limiting in that at least some of the folks working on that master testnet and supporting end users, they want to interact with more than one testnet at a time. So this vPoint tool uses an LD preload SOX client library called Dante Client. This thing basically is transparently wrapping itself around all of the socket calls that get made by programs run from that shell. So if we run SSH or our deployment tools or various other things that might want to make connections to machines in that private IP space, their IP communication is transparently tunneled through a SOX proxy that's running on that NAT gateway. So you start up this vPoint shell, you say vPoint my testnet, and now you can reach that IP space of that testnet. It feels as though it's local to you, even though, or reachable by you, even though it's kind of hidden behind this NAT gateway. Chrome vPoint and Firefox vPoint are basically the same idea. Let's easily start a browser that has the right SOX configuration to let the browser tunnel into a specific instance of one of these testnets. That's the testnet slide we looked at a moment ago. So, some information about kind of our system and our stack, and then I'll talk a little bit about the evolution of our system and the challenges that we faced. It's sort of a centrally managed system. So we grant resources to users and groups. We've got a stack of hardware in our lab in Quincy, Washington. It's all built on commodity hardware because Akamai is in the business of working with system integrators to design and build large numbers of commodity servers, middle-of-the-road quality and reliability. They're very cheap for us. So we started out by building the system on top of that. We've said, okay, if we need to switch to something different, we will, but this stuff's easy for us to get our hands on. So let's go ahead and use those server profiles that are available to us, use open source technology, see how far that will take us. And so far, I'm not sure I see any reason for us to change course. We really haven't worked heavily kind of at the level of optimizing our stack and getting performance out of our stack. A lot of our focus, as I mentioned, has been in building out our web application and getting adoption and building out our master testnet. But I'm sure that the VM layers are going to get a lot of attention in the future as some of the other sort of first order problems start to reach their long tail. So right now, our production cluster has about 55 VM hosts. Those servers are dual processor machines with 32 logical cores, 128 gigs of RAM. Our latest order, we're going to 256 gigs of RAM because we're a little cool on CPU and network. Two 10 gig Ethernet cards. about 40 to 50 of our Akamai VMs with their sort of ambient load tend to run happily on these machines. And as I said, I think there's room for more there with increased RAM. Our storage system uses machines that are a little bit more modest, again, still 10 gig. And so right now we have about 42 terabytes of usable storage, and we're bringing a lot more online in the next few weeks. So that supports about 50 to 60 testnets. The testnets are configurable, so these are sort of rough numbers. On the right-hand side, you can see right now our master testnet has grown to be 203 VMs. There's 200 VMs in our master testnet. If you clone the entire thing, you're firing up 200 VMs, which takes 430 cores, almost a terabyte of RAM. The only time we really clone that entire thing is when we're creating a master candidate and we're doing upgrades to create a new revision of our master testnet. Our individual users will slice that master. So they'll say, I need those core infrastructure systems and these other reporting infrastructure systems, and I need these 2 sets of edge systems. And all those other systems, those other 150 machines, they can just appear down, so just don't boot them. And so in reality, each engineer or automation job that wants to use Vtastic is going to use a lot less than what I'm showing there. As far as how the system's evolved, our initial version, I mentioned we're using QEMU KVM, and for storage, we've been using GlusterFS and working towards Ceph. So when we started, all of our QCOW2 images and their backing images were stored on Gluster and accessed through a fuse mount. That got us a long way, but we did have periodic loss of VMs, memory leak issues, and a lot of suggestion from everyone we talked to and all the investigation we did that Gluster wasn't really the long-term thing for us. My team sort of inherited the stack in this state, and as I said, it's actually worked quite well, and we haven't had to come around and put a lot of effort into it, but we will. So after the first iteration that had everything going through Gluster's fuse mount, then we switched to have QEMU use libgf API to talk to GlusterFS directly. We thought that was going to help us in terms of the bottleneck that the fuse mount would pose for all the VMs running on a machine, that we might get better reliability. Our experience was actually kind of the opposite. Once we moved to libgf API, we started having more VM deaths, and they were catastrophic, like the VMs were basically unrecoverable frequently. And we also continued to have some problems with the fuse mount because we were still using the fuse mount for image management. So after the libgf API foray, then we switched back to using the fuse mount to access the backing images, the snapshot images, but we put the scratch image, so the image that the running VM is writing to, we put that QCOW2 file on the VM host's local disk. And that's what we've been running with for the last year or so. That's worked pretty well for us. The cost there is snapshots take time because we have to move things out to Gluster. There's no path for live migration if we've got our scratch images on local disk and not on remote storage. We do still occasionally have fuse mount problems, and there was a period in the beginning after making this transition that we were still having problems with VMs dying. Those problems seem to have subsided. We were never really left with a solid explanation for why. It kind of left us wondering whether our actual issue was in the lab's network, but we were never able to really get to the bottom of that with the lab folks. For the last 13, 14 months, this has been running, pretty problem-free. We had a networking-related issue that was plaguing us in November. Sometimes we have outages. If there's a hardware outage, obviously, things like that. But we really haven't had much in the way of kind of unexplained outages where VMs are dying for really no good reason. So that's good, and it's taken some of the pressure off of the Ceph development work, which has been going in parallel with all of the web application development and master testnet work that we've been doing. So I'm glad that Gluster hasn't been biting us recently, but we still have this feeling that we need to move to Ceph and that's the right direction. And so that's our next step and what we've been working on over the last year. And one person sort of on the side has continued to push our Ceph capability forward in terms of getting it wrapped in all of the Akamai stuff so that we can set up an instance of all of our storage system, our VM hosting system, OpenNebula, and bootstrap all of that with Akamai's deployment tools, so it's very easy for us to set up for testing and for production. So he's got that into the right spot where we think we're ready for scale testing. To get that working, we did make some customizations to the OpenNebula drivers to change basically the way Ceph cloning works, because for our use case of managing these sorts of trees of snapshots and this master testnet idea, what we want to do is to take a given RBD volume and make a copy on write clone volume off of that. And I'm trying to remember now what the detail was. I think when we make that clone, you do get an RBD clone with the Ceph driver as it came out of the box. But then when you do a CPDS to save that clone, it would actually copy it and create a standalone image on Ceph. And what we want instead is to maintain that linkage so that we can then clone again and clone again and clone again and establish this sort of a tree, right? And a couple of things that we really want to get out of that are, first of all, the ability to do live migration. Getting everything remote would let us do live migration again. Also being able to do some form of flattening. Right now with QCOW2, we keep making these child clones, and when our backing chain gets to between 6 and 10 images long, we will export it and start over with a new backing chain, which means we have 2 copies of our master testnet sitting on our storage system. And you can't flatten QCOW2 images when there's VMs depending on them. Our system never quiesces. There's VMs depending on those images at all times, so we'll never have an opportunity to flatten. It appears that with Ceph, we can at least flatten from the top down. So if we could just throw away our oldest master and keep adding new masters on the leaves of the tree, that'll serve us well and help us a lot in terms of the way we manage that master. And then some future possibilities that we have in mind, include an idea of incorporating physical hardware into these VLAN isolated private networks that I showed. So can I boot a clone of Akamai and have all this virtualized Akamai stuff running there and have that infrastructure supporting a physical machine so I can drive load at that physical machine and see how that physical machine behaves. Adding some TC capabilities to do realistic networking conditions, adding the ability to define, to do some inter-networking within that VLAN space or within that private space, and being able to have some sort of a multi-site feature that would allow us to do smart replication of our snapshot data. I mean, as I showed before, our master is about 2 terabytes in size, so we don't want to replicate that globally. We really are a kind of a local system, but we'd like to be able to selectively move that data to a faraway geo. And so I think, who was it this morning that was talking about, exporting diffs and moving diffs around? Was it Justin? Yeah. And so that sort of idea is what we have in mind for after we get onto Ceph. So that's all I have. I'll take any questions if there are any.